Okay, so we're looking in 6.4 at some application problems where we have some kind of an exponential function involved in a word problem, and we're going to need logs to be able to solve it. And one of the reasons we know that is because if we need to solve for the letter that is part of this exponent right here, we're going to go ahead and have to convert to logs to go ahead and get that answer. There's no way I could just put if I don't know h, I'm not going to be able to evaluate this in my calculator. Okay, so let's read the problem. It says a drug medication is described by this formula, and it can be used to find the number of milligrams D of a certain drug that's in the patient's bloodstream each hours after the drug was administered. When the number of milligrams reaches 2, the drug is to be administered again. What is the time between injections? In other words, what is the time at which the number of milligrams reaches 2? Now remember, D is the milligrams of drug, so we know D, we don't know H. So let me go ahead and rewrite this here. I have then, if I substitute 2 milligrams for D, I'll have 2 is equal to 5e to the negative 0.4 h. And what I have is a situation where I am needing h, which is in an exponent, and the only way I'm going to do that is convert this to a logarithmic equation. And so what I'm going to do is I'm going to isolate the exponential part of the equation. I'm going to go ahead and divide by 5 on both sides. So I have this. Okay, now I can convert to a natural log. Remember, an exponent's always the output to a log, so I'm going to say the natural log of 2/5 is equal to negative 0.4 h. And now I'm going to go ahead and divide by negative 0.4 on both sides. And this, if I put that in my calculator, should be our answer. So let's go ahead and take a look. So what I'm going to do is I'm going to go ahead and take the natural log first, and then I'll just divide here. So let me show you on this calculator. I'll go ahead and hit the natural log button right down here, right here, natural log, okay? And then I'm putting a fraction there. I'll use my fraction feature alpha, y equals. I'll put 2/5 in there, 2 and 5. I'll go ahead and close the parentheses. And then I'm going to divide by negative 0.4. And that should be exactly what I see here. And let's see what we get for an answer. And by the way, you can see here, I got this problem right out of our book, and there it is. It does say it should have been 2.29, or 2 hours and 17 minutes, right? 2.29 hours. 2.29, let me see it, yeah, hours, right? Okay, so that's that problem right there. Let me just go ahead and record the answer here, and we'll try the second one that I have here on the sheet. So H is equal to 2.29 hours. Okay, let's try this other one over here. So let me switch over here. All right, let's read this. It says the equation governing the amount of current in amperes after time t in seconds in a simple RL circuit consisting of a resistance R in ohms and an inductance L in henries and an electromotive force of E in volts is given by this formula right here. So if you take a look here, we got a lot going on here, right? There's capital E, capital R. This E has to do with a natural log base, right? And here is capital R, capital L, and then there is time right there. So we're going to have to draw a lot out of our problem in order to go ahead and plug all these values in here. And let's take a look. I would get here I is equal to, and then if we take a look, we have it says if E is 12 volts, so we'll put 12 in for capital E, and the resistance was 10 ohms, we'll put that there, and then we close the parentheses, and I'm just following along here. That's a constant 1 minus E, and then it's to a negative exponent, so that's the sign right there. And then I have R divided by L times T. So once again, R was 10, L was 5 henries, and then T is unknown. Okay, so what we got here is this situation right here, right? Now, it also says, how long does it take a current of 0.5 amperes, does it take to obtain a current of 0.5 amperes? So that 0.5 amperes, remember, the current was in amperes. So I'm going to set the equation equal to 0.5. So I could rewrite this again if you don't mind, just to save some time. I'll erase I, and I'm going to substitute 0.5. And by the way, this problem has you do it at 0.5 amperes and then at 1.0 amperes right here. Okay, so now it looks like I have to go ahead and try to isolate this exponential part of the equation, and then I'm going to convert it to logs, because what I'm after is an unknown that is in an exponent. The only way I'm going to get to that is getting it to be converted into a log problem. So let's take a look here. So I could go ahead and clean things up here a little bit. I think I'm going to call this 1.2 right here. And then I'm going to distribute that 1.2 across here. And my goal here is to isolate this exponent part, like I said a minute ago. So this is going to be 1.2 times 1 and 1.2 times E, and I could call 10 over 5 2. So I have this and make it a little progress. I'm going to go ahead and I'll subtract this over here, right? Remember, this is subtraction here. I'm not dividing then, I'm subtracting this to both sides. So if I subtract 1.2 from both sides, I'll get a negative 0.7 on the left and a negative 1.2 e to the negative 2t on the right. And all I have to do now is divide by a negative 1.2, which now makes this positive. And I have 0.7 over 1.2 is equal to e to the negative 2t. And now I am ready, let me move this up a little bit. I am ready to go ahead and convert this to a log. So I first tried to isolate the exponential part, and now I'm going to convert it to a log. So we know always that the output to a log is the exponent. So I'm going to say negative 2t is equal to the natural log, because we had a base of e, of 0.7 over 1.2. And then I'm going to go ahead to isolate t, just divide by a negative 2. And I'm ready to put that in my calculator right there. So let me go ahead and use my calculator. It looks like a pretty similar calculation to what we did over here. And so we're going to go ahead and this time use the natural log. So I have the natural log of, and I could go ahead and put that in as a fraction. I'm not even going to use the fraction feature. I'll just go 0.7 divided by 1.2, close the parentheses, and now, because I did have a fraction here, dividing by negative 2, and this should give us our result. And we got 0.269, right? And that should be the time. And take a look here. There happened to be an answer key in my book, and you could see that if I rounded this off, this would be the same as what we have right here, 0.2695, and let me see what the units are in seconds, 0.2695 seconds.